In this video, we're going to look at forces that cause acceleration in circular motion. Remember, in uniform circular motion, the velocity at any point is tangent to the circular path of the object. The object is also moving at a constant speed. So for velocity to be changing, the acceleration must be inward. We call this radial acceleration because it is inward along the radius. We also may call it centripetal acceleration, centripetal meaning center-seeking. Now we know from Newton's laws that for an object to be accelerating, there must be a net force on that object. When this net force acts to cause an inward radial acceleration like this, we call this centripetal force. We know the radial acceleration has a magnitude of v squared over r. Using Newton's laws, once we find the net force, we can set this sum equal to the mass times this radial acceleration. It is important to note that centripetal force is not a new type of force that we identify in a problem and then include in our sum of forces or in our free body diagram. The net force itself is centripetal, which means it causes a centripetal or radial acceleration. The centripetal net force is due to a force or multiple forces that we're already familiar with. For example, if you tie a string around a rock and you swing it around your head, the tension in the string is constantly pulling the rock inward, causing it to change directions. In this case, the tension is causing or providing the centripetal force, leading to the circular motion. Let's look at a couple of other common examples. Let's imagine you're driving your car around a curve or in a circle. There must be a force acting on the car that keeps it going in a circle. In this case, the centripetal force is provided by static friction between the tires and the road. This friction keeps the car from sliding outward. If you were going in a circle and the road suddenly disappeared and was replaced with ice where there is little friction, the car would start to slide in a straight line since there would no longer be friction to apply this force and change the car's direction. Another example is the Earth going around the Sun due to the gravitational force of the Sun pulling the Earth toward it. This is a force we'll discuss in more detail later. If the Sun were to disappear, the Earth would continue to travel in a straight line. The Earth's gravity also pulls on the Moon in the exact same way. Until now, anytime we've had forces in a problem, we typically use Newton's laws to solve these problems. In this case, we have forces in circular motion, so let's see how this affects our problem-solving process. And then we'll look at example problems to practice. As always, our first step will be to draw pictures and free body diagrams. However, we may need to do this from multiple views or perspectives. For example, we may want a side view as well as a top-down view if the circular motion is horizontal. Next, we want to sum the forces in all directions, but in circular motion, we tend to use what's called an RTZ coordinate system. R is the radial direction, T is the tangential direction, and Z is the vertical direction. We do this because only the net force in a given direction will affect the acceleration in that direction. This means we want the net force in the radial direction to get the centripetal force. The tangential direction is always perpendicular to the radial direction, so it would make it easy to break forces into radial and tangential components the same way we break forces into x and y components. Also, in uniform circular motion, there is no tangential acceleration, so we know these are zero. When we have the net force along the radial direction, we set this sum equal to the mass times the radial acceleration, which we can write as v squared over r. Now let's look at some examples to see how this works. In the first problem, you attach a rope to a 30-kilogram cart. The rope is 2.5 meters long, and you use it to spin the cart in a circle, keeping the rope parallel to the ground. The tension in the rope is 150 newtons. Find the angular velocity of the cart in RPMs or revolutions per minute. Let's begin by drawing both a top-down view and a side view. The cart goes in a horizontal circle, which we can see from above. This view still does not show the forces that are vertical, but we can see this in a side view. We'll also draw two free body diagrams. From top down, we have a tension force from the rope pulling the cart inward. The direction of the cart is moving tangent to the circle, so the tangential axis is perpendicular to the radial axis. On the free body diagram from the side, the normal force and weight will be on the vertical z-axis, and the tension can be drawn along the radial direction, parallel to the ground. Also, notice we have essentially drawn our picture and free body diagrams at a moment in time. We know the motion looks the same at all points around the circle, and the forces will maintain their directions relative to each other, so we can choose a convenient snapshot, if you will, that will make our forces easy to account for. Now we can move to summing the forces. For the z direction, we just find the normal force is equal to the weight. This may be useful for problems where there is friction, but in this case we're neglecting friction. For the radial direction, we only have the tension. Notice we have chosen our positive radial axis to point toward the center of the circle. This is useful because it will also make our radial acceleration positive since it is inward. The tension represents our centripetal net force, so we will set it equal to the mass of the cart times its radial acceleration, which again we can write as mass times v squared over r. We could also write our radial acceleration in terms of the angular velocity and solve for it straight away, but I'll solve for the tangential velocity v and then get the angular velocity from there. Solving for the tangential velocity v and plugging in, we get a speed of 3.54 meters per second. Now we can use the relationship v equals r times omega to solve for the angular velocity. Doing this and plugging in, we get the angular velocity as 8.85 radians per second. Anytime we use units of meters and seconds to solve for an angular quantity, know that the result will come out in terms of radians. So we will still need to convert to revolutions per minute, and when we do this, we get 84.5 RPMs. Now let's look at another problem similar to our example earlier. We have a curve in a road that forms part of a circle with a radius of 45 meters. If you drive a 1,300 kilogram car around this curve, find the maximum speed you can go without sliding. Take the coefficient of static friction to be 0.8. Again, we'll draw a top-down and a side view. The top-down view shows the horizontal circle with its radius. On this free body diagram, we can draw the force of static friction that keeps the tires from sliding sideways. Now this is not friction associated with the tires going forward in the tangential direction. The tires are not sliding sideways or side to side, and since they are not yet moving like this in this direction, the friction is static rather than kinetic. Now we can move to the side view. From this view, we can draw the normal force upward and the weight downward. Summing the forces in the vertical z direction, we find the normal force is equal to the weight, or mg. Now we can move to the radial direction, where static friction is pointing inward in the positive radial direction. Setting this equal to mass times radial acceleration, we can substitute our formulas for static friction and radial acceleration. Here, static friction is equal to the coefficient of static friction times the normal force, because this is the maximum value. The maximum speed occurs when static friction is maximum. As the speed increases, the centripetal force caused by static friction must increase to cause the radial acceleration needed to keep the object going in a circle. Since static friction can only increase up to some maximum value, this max friction corresponds to some maximum speed. Now we can solve for the speed and plug in. Notice the mass cancels, meaning the mass of the truck doesn't matter. And when we plug in, we find the maximum speed to be 18.8 meters per second. In this next problem, we'll have an object moving in a vertical circle. You swing an 8 kilogram bucket of water around a vertical circle. Find the minimum speed you need to swing the bucket so the water does not fall out if your arm and handle of the bucket form a radius of 1 meter. For this problem, we only need a side view. However, we will want to draw the side view with the bucket at the top of the circle. We will treat the force of your arm pulling on the bucket kind of like tension in a rope. Now, intuitively, we know that if we swing very fast, this will require more force. So to find the minimum speed, we need to find the minimum force downward when the bucket is at the top. Well, the bucket already has a weight pointing downward. So the minimum centripetal force on the bucket at the top occurs when there is only the weight of the bucket. Since the bucket is moving tangent to the circle, it will keep moving without falling at the top. This means you spin the bucket just fast enough that you don't have to pull on it at the moment it's at the top. Then as it passes through the top and falls through this highest point, you kind of catch the bucket and supply more tension to keep it rotating on the way down. Let's look at the forces on the bucket at other points of the circle. At the bottom, the bucket still has a weight pointing downward, and there must be tension in your arm pulling up on the bucket in order to not only cancel the weight, but a little bit more to cause the centripetal acceleration to keep it rotating. When the bucket is at some angle, we can rotate our axes to match the bucket. The weight is still straight down. Now some of the weight has a radial and tangential component, so the force that you need to cancel out the weight is less. Since the weight has a tangential component that is acting to slow down the bucket as it goes up, this means our motion is not uniform and the speed will vary at different points along the circular path. This is okay because we really only care about the motion at the top. I'm just going through the rest of the circle so that you know why it's important we choose the top position. Looking at the bucket when it is to your side and your arm is parallel to the ground, your pulling force is providing all of the centripetal force and the weight is all tangential, again slowing down the bucket. As the bucket passes through this point, the weight becomes more radial and begins pointing toward the center of the circle. This means we need to apply less force since the weight is helping, though it still has a tangential component slowing the bucket down. At the top, the weight is completely radial, so there is no tangential component. This means the bucket will be its slowest at the top. The weight will again start to accelerate the bucket after it passes through the top. And this is why we look for the minimum speed at the top. Again, if there is any pulling force from our arm, the greater net force would correspond to a greater speed of the bucket. We set the weight equal to mass times radial acceleration. Here the mass will again cancel, and we find the minimum speed only depends on the radius of the circle and the value of g. This also makes sense because if we were to apply more force at the top, it would be as if we were trying to pull the bucket inward, making a smaller circle, causing it to go faster. Plugging in a radius of 1 meter, we find the minimum speed is 3.13 meters per second. Now let's look at an example where you swing a 1.5 kilogram rock around your head in a horizontal circle using a piece of 1 meter long string. The string is weak and will break with a tension of 220 newtons, and we want to find the maximum RPM at which we can swing the rock without the string breaking. From the top, the rock makes a circle with a radius r. Here we can see the tension seems to point along the radial direction. However, we also need to look at the side view. The string and rock will make a slight angle with the horizontal, and we'll call this angle theta. If we think about it, this must be true, because if the tension were completely horizontal, there would be no vertical force to cancel the weight of the rock, and this means the rock would accelerate downward. So in order to keep the rock in a level horizontal circle, there must be an upward component of the tension to cancel the weight and keep the rock from accelerating vertically. We will draw our tension at this angle, and we need to be careful with our radius as well. We were given the length of the string, so this is the diagonal length from your hand to the rock at the edge of the circle. We can form a right triangle and find the radius of our circle using the length of the string times cosine of this angle. Since the components of tension will depend on this angle, we will need to find out what it is. We can do this by summing the forces in the vertical z direction since we know the mass of the rock and can find the weight. Here we have the z component of tension upward and a negative weight. We can move the weight to the other side as mg, then divide by the tension and use inverse sine to solve for the angle. Doing this gives us an angle of 3.83 degrees. Now we can move to the radial direction. We only have the radial or horizontal component of tension. This is applying our centripetal force, so we set it equal to mass times radial acceleration. Here again, we need to be careful not to plug in 1 meter in for the radius. Instead, the radius is equal to this length times cosine of theta. Solving for the radius and plugging in, we get 12.1 meters per second for the maximum speed. We're asked for the maximum angular speed in RPM, so we need to first convert to radians per second. Here, our value of r is very close to 1, so we also get 12.1 radians per second. Converting this to RPM, we get 116 revolutions per minute. Faster than this, and the string will not be able to provide enough force to cause the radial acceleration needed to keep the rock going in a circle. Now let's look at a car going around a curve, but the curve is now banked. In this case, the curve has a radius of 160 meters. If we want to be able to take the curve going 30 meters per second, we want to find the angle of the banking needed so that the car will not slide outward in the absence of friction. If we draw a free body diagram, we'll do this from the side. The circle the car is going in is horizontal. It's just that the car is now rotated at an angle or is leaning as it goes around due to this banking. So we'll leave our radial direction as horizontal and our z direction is still vertically upward. The weight of our car is straight down and the normal force is perpendicular to the surface of the highway, which I'll represent as a yellow line for reference. Notice the angle of the banking is the angle between the normal force and the vertical, not the horizontal. On a flat road, the normal force would align with the vertical, perpendicular to the surface. Since we rotated the surface of the road by an angle theta, we also rotated the normal force by the same angle from the vertical where it was. We can imagine the car is traveling in a straight line, and then the highway begins to bank, causing the car to turn. If the highway is not banked enough, the car will be traveling too fast and slide right off the bank. The normal force from the bank has a radial component that causes the radial acceleration needed to keep the car going in a circle. Remember when we did not have a banking at all. We needed static friction from the tires and the road to provide this inward force. In this case, if the car goes too fast, we would need static friction on the banking as well. Here we are looking at the angle that is just steep enough that we can make the turn without the help of friction. We will begin by summing forces in the vertical direction. We have the z component of the normal force, found by using cosine, and a negative weight. Solving for the normal force, we get the weight mg over cosine of theta. Now that we have the normal force, which is causing our centripetal force, we can look at our radial direction. Here we only have the radial component of the normal force, so we set it equal to the mass times radial acceleration. Plugging in the normal force we just found, we see the mass on both sides will cancel. We also have sine over cosine of the same angle, so we can write this as tangent of theta. Now we can divide by g and take the inverse tangent of both sides to solve for theta, and find the banking should be at an angle of 30 degrees. At this point, hopefully you're starting to see the similarities of solving these types of problems when there is a centripetal force to solving force problems with motion along a line. The overall process is the same, but we sometimes need another view to get the whole picture. Then we use a convenient set of coordinates that work better for circular motion. We draw a free body diagram and apply Newton's laws in the same way, but now we may have radial acceleration when summing up forces in the radial direction. We'll look at the force of gravity and non-uniform circular motion where objects are speeding up as they move around in later videos. So that's it for this video, and I'll see you in the next one.